Alright, welcome back to the algorithm analysis slides. Let's finish these up today, and then we'll also start some new ones. So at the very end last time, we were finally getting into how we can use our big O's, big omegas, big thetas to describe the complexity of an algorithm. Okay, so we talked about there's a couple different kinds. We usually care about time complexity and space complexity, right? And yeah, we just gave a little example. Let's go in depth into that idea of algorithm complexity. So usually when you write an algorithm, there are certain times where it's going to run really fast. It's like your best case. There are times when it's going to run super slow. That's your worst case. And then there's times in between. That's called your average case. So these terms, I'll define them for you specifically, but they mean what you expect. Okay? So yeah, the three most common ways of looking at an algorithm and describing how complex it is these different viewpoints. Like what's going to happen in the worst case when nothing goes your way, your enemy picks the input for your function or something, and it takes the most amount of time or the most amount of space, whatever you're trying to consider at the moment. And this is probably the most important analysis way that you need to learn. And that's what you've been learning essentially in CSCI 41 anyway. This is worst case analysis. Like, when is this going to take the worst, longest amount of time, for example? That's worst case. Oops. Next we have best case. That's when everything is going your way and you take the least possible amount of time for your algorithm, or the least possible space if it's a space kind of analysis. So that's the best case. And then the average case is in between. Average together all the different possibilities for how your program might run. That's your average case complexity. That is not the topic really of this class, though I'll hint at certain average cases. But an algorithms class is where you're going to learn the tools to hit the average case harder. Okay, so look forward to that at a four-year college. So yeah, let me give you an example of these three ideas with binary search trees. So let's determine the worst case running time for a binary search tree search algorithm. And it's going to be in terms of the number of nodes in your tree. So here's an example tree, right? This is your root, and I don't know, maybe you're trying to search for some value, and who knows, right? I think in the worst case complexity is you're looking for something in your tree and it's not there. You have to go down as far as possible. You see how that's going to be your worst case? So maybe you're looking for 5, which would have been here, but it's not. So that's kind of the worst case. How long does it take to get to the bottom? Okay? And so if you remember, you could have a really horrible looking tree. All right, let's pretend there's n elements in the tree. You can have a really horrible looking tree, and the thing that you're looking for may not be there. And so do you remember that you can have a horrible looking tree like this if you insert in a weird way, right? And then there's n things in this tree, and you're looking for something that would have been right here. That's the worst case. That's the worst case for binary search tree search. All right, this is going to take n+1 comparisons. And every comparison is constant time. So this is going to be theta, right? Big theta of n. This is going to be a linear time issue trying to search for something in a binary search tree that is ugly and looks like this. So the tree is essentially a list at this point. That's the worst case for a binary search tree. Tree is a list. And on top of that, the value that you're looking for is not there. All right, that's a little silly, but that is your worst case. You have to go through every single node in the tree, all n of them. All right, theta of n. And all right, let's talk about the best case. When everything goes our way, how fast could binary search be in a binary search tree? Searching through a BST. Well, pretend we had this tree, and the value that we were searching for was 8. Do you see how you'll immediately find it by just comparing the root? That is a constant time amount of things to do. Just compare one thing. So in the best case, if the thing that you're looking for is at the top, it is a constant time algorithm. You will almost never get here, but it's good to understand that. You see how that's going to be your best case. And then average case is what's in between. So on average, maybe you remember this from CSCI 41, on average your tree is about balanced, and you're looking for something at a leaf, and it all averages together to be about logarithmic time. Okay, so if you have a perfectly balanced tree and you know that, then it is guaranteed to be logarithmic time. So log base 2 of n really, but we know that we can get rid of the base 2. So usually we just say big theta log of n for your average case, because it's a binary search tree that is balanced, essentially. The average BST is more or less balanced, and then you get logarithmic time when it is. Okay, so that's the ideas for those. Let's keep on chugging with this analysis train, and let's talk about some code that we've already written. So you've had to write is prime a couple times now. Do you remember that algorithm? It's essentially a loop, right? It's like for I starts at like 2 to, you can break it down to be like, you can go to x minus 1, or you can go all the way to square root of x. That's how you can do it as efficiently as possible, because you're looking for only one factor. And then what you do, right, in is prime is you check, and you see if the thing that, like your current I value, check if I divides x, because it's like x that we're trying to determine if it's prime or not. Check if I divides x, and if it does, then we found a factor that's not 1 or itself, and we'll return false if so. And then otherwise, we'll, at the very end of this loop, we'll return true. Like we've given them all a try, we have not found any factors, and so it must have been prime. All right, so that's our is prime function, essentially. And so, all right, this is a loop. Return true is constant time. This is a loop, and all right, we have to check how many times is it running its body. So it's going to run its body square root of x minus, like square root of x to 2 is like square root of x minus 2 plus 1 times-ish. So it's about square root of x times. And then what's it going to do in its body? How much work is it going to do each time it runs its body? Well, that's an if statement, right? Checking and returning false. So that's constant work in the body. Does that make sense? So that's essentially what's gonna go on. Maybe there's like, this is one basic operation and this is another basic operation, so it's like 2 basic operations in the body times doing that square root of x times, because it's going to loop that many times. And then at the very end, in the worst case, right, it'll return true. And that's one extra basic operation, essentially. So that's the kind of counting that you'll get in the hang of doing if you're not there already. And of course, this is big theta of square root of x. It's square root time, which is not something we normally see. Primality checking is all about square roots, believe it or not. That's kind of fun. All right, let's talk about some other ones. So calculate pi, remember that one? So what did we do? What was that function? How did we implement it? It was like, all right, we had to throw a bunch of darts, and so do num darts times, we had to do something. Do num darts. It's a little silly. Maybe it was 1,000,000. Do num darts times, all right, what did we do? We picked a random coordinate, right? Pick a random xy coordinate. Then we check to see if that coordinate is within the unit circle. Check if inside the unit circle. And then if it is, we'll add to our count, and eventually we're going to divide by some stuff, right? So that was add to count. And so at the very end of this, after this loop is all done, we are going to return some stuff, right? We had a count, and we counted how many times it was within this unit circle. Maybe that was A, and then the total count was num darts or something. So like our count was C, and then we divided by num darts. And then that was a good approximation for pi over 4, so we multiplied that by 4. And that's essentially the algorithm, right? So again, it's a loop. It's a loop that goes num darts times, and what does it do in its body? What is it doing? We're doing the worst case analysis right now, by the way, which I guess best case and worst case, there's no real difference to these ones. It's just, it depends on num darts. It depends on x. Let's see here. So pick a random xy, that's constant. Check is an if statement, constant. Add to count, constant. So that's constant work in the body. I'll say big theta of 1 now. And then to return at the end, just doing all that math again, it's constant work. And so it's really num darts that is the bottleneck here. You got to do all this constant work num darts times. And so num darts is your variable, right? This is theta of num darts time. And I should have used capitals everywhere, excuse me. That's the idea. Let me capitalize these while we're here. Num darts, there. And then finally, do you remember SAT solve? StatSolve was interesting. It's like you got a formula, and that formula had a certain number of variables in it. It was like x or y and not z, and so you had like x, y, and z, and you had to choose from every possibility of true and false for x, y, and z. So like you had 0, they could all have been false. Maybe x and y were false and z was true. Maybe x was false, y was true, and z was false. Like all of these possibilities, you have to try all of them. 0, 1, 1, dot, dot, dot. It's like a truth table, essentially. All the way down to 1, 1, 1. They're all true, so every possibility in between. And let's pretend that there's n different variables in your formula. You have to try 2 to the n options. And for each option, you check and see if the formula is true. And that's essentially constant work for the formula. And so it's essentially you're doing an exponential amount of work, constant amount of time. And so in the end, this is going to be a exponential time algorithm. It's pretty bad. But that's as good as people can do these days. And so that's a horrible graph if you graph 2 to the n, right? It grows so fast that you cannot solve a formula with a lot of variables in it in any reasonable amount of time. Okay? So that's just some practice with analysis. Hopefully it's making a bit more sense. And yeah, so let's talk about just wall clock time for a second, just so that we can get the ideas behind that and kind of understand why we don't really think about things in that way, but it's good to have a corresponding number value, right? So let's pretend that every instruction inside of our processor takes 1 microsecond, which is more or less accurate, especially if your programs are accessing RAM, because that takes longer than accessing things called registers. So we'll get there in CSCI 45. Just you wait. But let's pretend every instruction, every basic operation inside of a CPU takes 1 microsecond. And so here's what happens for each algorithm given its complexity. So here's like a logarithmic complexity, linear complexity, n squared complexity. If, and this depends on some input size, right, n. If n is 10, then like everybody's pretty fast. Even, exponential time. It still takes a millisecond. That's okay. That's really not bad. But once n gets to be 50, these all start like, you start seeing their true colors, right? So a logarithmic algorithm takes super fast. A linear algorithm, still a blink of an eye. N log n, still a blink of an eye. N squared, again a blink of an eye. N cubed, you can finally kind of as a human see the difference, see how long it's taking. But a 2 to the n algorithm, if every instruction takes this long, it's going to take 35 years. So a formula, right? Solving a formula with 50 variables. If you don't know any other tricks, you are kind of going to be sitting there for a while, okay? That's the idea. And then once these get large, I think you can see like the big differences here. N log n, like once you get to n cubed and above, like you're going to have a bad time, okay? So like 2 to the n, it's just a ridiculous amount of time, like longer than the universe has existed once you get to like 10,000 input size. A 10,000 size vector or something. Once you get to 100,000, it's, oh man, not even fun. So yeah, that's like a good comparison. I hope you see why you want to keep your algorithms efficient if you can. Like once you get to n cubed, you're kind of stuck. Okay, so you may have heard recently, a year or two ago, during the pandemic, the video game GTA 5. It had an online portion, and when it connected online, it had a horrible n squared algorithm that made the loading times really bad, and somebody fixed it. They converted it to a linear algorithm, which is funny. So it just goes to show, like, even fancy people in industry, they are not analyzing their algorithms very well. And so this is why we're learning it. Okay. So with all that, I have a question for you now. Here is an algorithm. It is called maximum subsequence sum. What it's going to do is it's going to find the maximum subsequence inside of an array. It's given an array, essentially, A1 through AN. So it looks like this. There's your array. You're given n things, right? And I want the worst case complexity. See if you can figure that out. So let me explain to you what's happening in this algorithm, first of all. So let's pretend that this is our array. Let's pretend it's got 5 things in it. 1, 2, 3, 4, 5. All right. So this is like 1, -2, 3, 5, -7. It's a cool little idea. A subsequence is when you have a contiguous piece of your array. So like from, let's say, I guess it's from like here to here, this is a subsequence. From here to here, it's a subsequence. It's just a piece of your sequence. All right? You can't skip over anybody. But the goal of maximum subsequence sum is to find, like, try every possible subsequence in a way, hopefully an efficient way, and give back the one that has the biggest sum of all the elements in that subsequence. All right? So for example, like here is a subsequence if you go from here to here, and the sum of it is like -2 plus 3 plus 5, so 6. So that's I don't know, a sum 6. That's a subsequence with sum 6. But that's not the maximum, because you can do this one, right? 3 plus 5 is 8, and that's going to be your maximum subsequence sum, right? And that's what it's trying to do here. It's trying to go through all these possibilities, figure out the maximum subsequence sum, right? So see if you can check what's going on here and give a worst case time complexity. And so n is the factor. All right. So assuming you've taken some time to think about that, let's go over it. Let's start counting some stuff. All right. I copied it onto a blank slide because there's a lot to write out. So let's go through all these things. Like, all right, this is the first line of the body of the function, right? So like this is of course going to be constant work. The return statement at the end, again, going to be constant work. The bulk of the work is happening in this loop, okay? So, all right, this outer one is going n times, so it's going to multiply its inner work times n. All right, so we need to figure out the inner work now. Okay, let's see, we have a this sum gets 0, that's constant work. And this is the kind of game you play essentially in your head. And then, oh, this one's from I to n, so it's different every time. So like when I is 1, like this is j now, it's depending on I. So when I is 1, the inner loop, how many times does it execute? It's going from 1 to n, so that's n times. So when I is 1, the inner loop iterates n times. Interesting. But when I is 2, it goes one less. It goes from 2 to n, which is n minus 1 times. You see that? What's going on? It's going to iterate n minus 1 times. And then when I is 3, it's going to iterate n minus 2 times. So it kind of gets smaller as you go. That's interesting. And then what does it do in its body? It's like, all right, it has an assignment statement in the inner loop's body, assignment statement, and then a comparison and an assignment. So just this whole thing, this body of the inner loop, that is going to be constant work. And it's going to go a different amount of time, which is weird. So I guess the main question for this analysis is like, how many times we're going to do this body? It's constant work, so we can just count and just keep the count as the answer, but how many times? All right, so that's going to be our goal, to determine how many times is this inner loop's body going to execute, because like this is going to be, and we're going to multiply that by n, right? Because we know this outer loop is iterating n time. It's just like, how many times we're going to do this times n, okay? So, okay, this one then, this line, because it's going to iterate n times, this becomes theta of n for the total. Does that make enough sense? This is theta of n for this one line, because it's iterating n times, okay? And then we got to figure out, like, what is this? How many times we're going to do this constant work? So if you think about it, we're going to do this body, we're going to execute that body. Well, the first time when I is 1, n times. The second time, n minus 1 times. The third time, n minus 2 times. All the way to when it's just I is n, so it goes j from n to n. It's just one time at the end there, okay? If you know some fancy math, there is a formula for how to compute like what this answer is. What is the sum from 1 to n of any number, starting at 1, going all the way to n? The answer is n plus 1 over, n plus 1 times n over 2, all that over 2, which is equal to, if you do a bunch of like multiplications, that's n squared over 2 plus n over 2, all right? So it's like, that's a 1/2 n squared and a let me write it that way actually. That's a 1/2 n squared plus a 1/2 n, and of course this term wins. All right, so this body in all its glory, how many? It's going to iterate. It's going to happen how many times? This many times. And it's going to do constant work each time, and so it's going to iterate theta of n squared times doing constant work each time. So this whole darn thing, this inner loop, is going to take theta of n squared work. All right, and that's for the whole loop, for like every time it runs total. So the final answer then, the final runtime analysis is it's going to be like constant plus n squared plus constant. And of course, the term that is n squared wins out. And so that's your analysis, okay? Theta of n squared. You may have looked and just saw, oh, doubly nested loop, n squared. And that really was true. Even when it starts at I and like it does a little bit less every time, it still evens out to n squared. There's just a nice small constant out in front of that. Okay, so that's why. That's why you can just kind of read it off, essentially, and say n squared. But this was the more correct analysis, I guess, I should say. Okay, I hope that makes enough sense. So that is the start of that, and yeah, that's algorithm analysis in a nutshell. I would now like to talk about something called finite state machines, which is something I talk about in my CSCI 40 class. It's a fun little example, but if you've never seen it before, I would like to be the first person to show it to you. So a finite state machine is a very powerful concept. It's a model of a program, and if your program looks like a state machine, it's very easy to get the program right once you've drawn it out. So it's just a bunch of circles and arrows like everything else in computer science. But here's what a finite state machine is. It is an abstract model of some system, all right? And so it has a bunch of things called states. Those are the circular things, like that's an even state, an odd state. This is the Q0 state, the Q5 state. So those are states. And then transitions are ways to move around between states. So there's always a concept of where your current state is, and there's a way to move around, right? So on the input 1, starting in the even state, you transition to the odd state. On the input 0, starting in the odd state, you transition to the even state, okay? So you can move around between states in a finite state machine, and finite state machines, they must have a start state. That's like where you start out when you haven't gotten any input yet. So that's like, it's this arrow from nowhere. That's telling you where you start. So like we start in the even state in this machine. We start in the Q0 state in this machine. And then you may optionally have some final states or accepting states. That's where places you would like to end up, okay? So like you put a double circle for a final state. So this is the even state. It's a final state, but odd is not. You see that? And then this one has no final state. It's just fine. It's happy. So yeah, for example, this first one is a finite state machine that accepts only even binary strings. Okay? Let me explain that to you. An even binary string is something that's a multiple of 2. It's an even number. It's an even binary number. This is accepting 1s and 0s only. A binary number only, and it's going to be happy once it ends up even. Okay? And so let me kind of walk you through how this is going to work. Okay? So the bit string 0, 1, 0, that's that corresponds to the number 2 in binary, right? And that's an even number. And so let's run it through the state machine a bit at a time from left to right and confirm that it's going to say that yes, it's an even state. Okay? It's like, okay, we start here in the even state. We input our 0, and we stay there. We're still in the even state. We input our 1, and that's going to move us to the odd state. And that makes sense, kind of, because the number it's seen so far is the number 0, 1, which is 1 in binary. That's odd. And then finally, we're in the odd state. We see another 0. That is going to put us in the even state, and that's an accepting state. You see how that's a state with 2 double lines? That's the state that we wanted to be in. So it's accepting this string, indicating that was an even binary number. Okay, so you just run each bit in order. It's just like a string. Okay, and this is going to work. This is going to confirm that all the numbers that we know are even, or really are. This is a very simple way to figure out if a binary number is even. It's essentially keeping track of, does it end with a 0? If you think about it long enough, that's what's going on. It's like the number 0 in binary, that is going to, of course, that corresponds to our normal decimal number 0 as well. And if we just run that, like you give it a 0, it's even. It knows. So it's like, I accept that. The number 0, 1, though, in binary, that corresponds to the number 1 in decimal, as usual. And that is odd. So like, okay, 0, still even, 1, now we're in the odd state. And that's not an accepting state, indicating that this number was not an even number. Okay? That's the idea. And just any other number that you can think of, like 1, 1, that corresponds to 3 in decimal. It's like, okay, 1, 1. It's odd. Of course, it doesn't end with a 0. It can't be a multiple of 2 otherwise. But like 1, 1, 0, ooh, that's the number 6. When it ends in a 0, that's how you know it's even. In binary, that's a trick. So again, 1, 1, which was our 3, but we're in our odd state, but we have a 0 at the end of that. So we transition to the even state, and that is an accepting state, indicating that, yes, this was an even number. Okay, so that's an example finite state machine that like does something and tells you if it liked your input. Another state machine is this example, and what it does is it has an output as well as inputs. All right, so you start here. You can only transition. It's supposed to be a model of like an old style vending machine that took only nickels. You only needed 20 cents to buy something, apparently. And so you put in a nickel, and it transitions you to this state, but there's also a concept of an output. So there's no output on this state. But once you put in 1, 2, 3, 4 nickels, you transition from Q 15 cents to Q I have 20 cents now. And oh, sorry, it needs 25. Excuse me. It wants 25 total. It just doesn't need that state. So you put in 4 nickels. You've put in 20 cents so far, and then you put in 1 more nickel, and the output finally goes from none to I'm going to give you your candy or something. Okay, does that make sense? That's modeling. You need exactly 25 cents to get something, and there's an output involved. All right. So like these mark the inputs. They're next to the transition. So this is like the inputs. And these are the outputs after the slash. That's how your book displays it, at least. Outputs. Let's see what else. And then, yeah, you start in the I have no money in the machine yet. You put in a nickel, and you move to the I have put 5 cents into the machine. Q5 is what we're calling it. And the output is none across that transition. You get no candy yet. You haven't put in enough money. But then you put in more and more. And eventually you transition to Q10, Q15, Q20, and when you're in Q20 and you insert 1 more nickel, it's going to give you something as an output, finally. Okay? That indicates that it got what it needed, and it can give you the output that you wanted, like your candy or something. Okay? So that's a finite state machine, and they're just, I don't know, they're circles and arrows, and we can model this mathematically. Okay? Here's the fancy way to model it mathematically. Technically. So a finite state machine, it's a group of 5 things. We call it a 5-tuple. It's these 5 things. Capital Q, Q naught, I, A, and delta. That's the Greek lowercase delta. So, okay. Q is just your list of states. How many states, what are the states that make up your state machine? Let's model, for example, the even odd one. So Q is just what are the different states. We have an even state and an odd state. So Q for that one would be even and odd. Just give them names like this. All right. And this, if we write this all out, it's going to spell out exactly this machine. That's the idea. We're talking about the essence of any state machine now. What do we need to describe it? And then Q0 describes your start state. It needs to be, of course, an element of Q, which is all of your states. Q0 better be one of those. But yeah, our starting state in this state machine is the even state. And that's what that arrow's taking us to. So Q0 is the even state. That's where we start. And then, okay, I stands for all the different actions, or the inputs that you could see. Finite set of input actions. It's what is going to make something transition. So all the inputs are just the names along these arrows. Like you could input a 0 or a 1 from each state. A 0 or 1 from that state, and a 0 or 1 from the odd state. So your inputs are 0 or 1. Those are what you get to choose from and feed into the machine. 0 and 1. And then optionally, it could be empty, but you may have a set of accepting states, a set of final states that you want the machine to end up in, and you want to accept those inputs. And so the even state, and only that one, is the one state we want to accept. But you could have multiple accepting states, so we make this a set, And so it's just the set containing the even state. That's the only accepting one in this particular state machine. But you can have multiple, like maybe even and odd or accepting or something. That's the idea there. And then finally, probably the most important one, is delta. Delta is your transition function. It tells you, all right, I'm in even and I saw a 0, where do I go? You're supposed to stay in even. All right, I'm in odd and I saw a 0, where do I go? Oh, you're supposed to transition to the even state now. You got to move. So to describe that, you need a function. Given your current state and the input, where do you go to? So you're taking a tuple, you're taking two things, a pair of where you are and what you saw, and then delta is supposed to spit out where you're going from there. All right? So here's how we'll define the delta function. You can define a function as a pair of inputs and outputs, of course. So for example, we need to say like what's going to go on, what's going to happen if the input, if our current state is even and we see the input 0, like what do we put here? Yeah. So if we see 0 and our input is even, we stay even. We stay in the even state. So that's our output of this function. Oops. We stay even. You see that? That is how we're going to define this function, just for every possibility. All right, and if our current state is even, but we saw a 1, how do we move? Well, the transition better take us to the odd state. Our output along this path better be odd. And this is just how you write up this idea. The alternatives are, okay, we're in the odd state, we saw a 0, what do we do? We're in the odd state, we saw a 0, well, we should move to the even state. So that's what the transition function better give me back. We better move to the even state, okay? And then finally, last option, if we are in the odd state and we see a 1, well, we're still odd. So the output is odd. And so that is going to be our transition function delta. It's just like given where you are and your input, where do you go? You need that because that is going to specify these 5 things in total. I think you can convince yourself of it, right? They're going to specify exactly what it means to be a state machine. That specifies exactly what this state machine does, where it starts, where it goes, what its accepting states are. That's the goal, all right? So we have we formalized what it means to be a state machine, all right? And so with that, I'd like you to try this. So here is a state machine as an example. Here is one. I would like you to figure out what's going to happen for each of them. Actually, I've given you 2 state machines, excuse me, FSM1 and FSM2. They both take only binary numbers as inputs. See if you can figure out the outputs, all right? Or not outputs, excuse me. See if you can see if it's a string that the state machine likes, if it ends up in an accepting state after you've gone through them all, okay? So that is going to be the goal. And also, tell me where it ends, like maybe like the number, it was just 0 and then a 1 or something, like you end up in state D. So say what state you end up in, and then also if it was an accepting state, okay? So that's going to be your goal. Go through each of these strings, and for each of them, for finite state machine 1, show me its ending state and its output, and by output I mean is it accepting, ending state and was it accepting, for all of these. Finite state machine 2. Show me the ending state if you run this bit string through this one, and also was it accepting or not. So was it a double circled state? Okay, so give that a try. Maybe I'll do this first one for you through finite state machine 1, and then I'll let you do the rest. So finite state machine 1 is going to take 1, so we start here, right, we're in A, takes a 1, moves us to B, 0, 0, 0, so 0 moves us there, another 0 keeps us there, a third 0, still in C, and then 2 1s, so a 1, and then another 1 keeps us in B. So that's where we end up. We end up in the state B, and B is not doubly circled, so it's not an accepting state, and so I'll just put like an X or something. That's going to be our goal. All right, so try the rest, please, and then I'll show you my answers. So, yeah, for finite state machine 2, I'll just do it slowly this first time, and then I'll do the rest fast. So we start here, and we see a 1, so 1. Then we see a 3 0, so 0, 0, 0, so we're back in B. And then we see 2 1s, so 1, 1, and we stay in, oh shoot, I think I messed up. Excuse me, let me try again. My notes differ. So we start out here, we saw a 1, so we're in B, and then we see a 0, a 0, a 0, there we go. I think I forgot the third 0 somehow. And then we see 2 1s, and that keeps us in A. And that's an accepting state. So that's the end. So A, and it was accepting, yay. All right, so let's do the rest real quick. So this is the starting state for finite state machine 1. Maybe I should just stick to 1 at a time. This is like 0, 0, 0, 0, so it really doesn't like. Once you see the first 0, it's just never going to take you anywhere else but D. So you're going to end up in D there, and D is not an accepting state. Only C is for this first one. All right, let's try this one through finite state machine 1. 0, oh shoot, we're in D again. 0, 1, 0. It's unhappy whenever it starts with a 0, I guess. And then 1, 1, 0, 0. Shoot, I forgot to erase this one. 1, 1, 0, 0. Okay, 1, 1, 0, 0. So it's happy. And we end up in state C. And that one is accepting for finite state machine 1. All right, let's do the rest for finite state machine 2. So 4 zeros. We see 0, 0, 0, 0. Okay, we end up in A again. Cool. And so that is accepting. And then 0, 0, 1, 0. All right, 0, 0, 1, 0. And so I think we end up in C there, and that's not accepting. Darn. And then 1, 1, 0, 0 for this one. So 1, 1, 0, 0. We end up in D, and D is unfortunately not accepting. Okay, so that's finite state machines in a nutshell. They can represent cool ideas like this, and like it tells you exactly how your program could move around, and that gives you some very strong guarantees about the correctness of your program. So if you can make your program, if you can model whatever you're doing as a state machine, definitely do it, because it's easy to implement one of these in code. Okay, and I encourage you to try. So that's algorithm analysis, and I would like to start another set of slides before we go. So let's switch gears to a topic called induction and recursion, and oh man, we're going to be here a long time because there's a lot to talk about. It's probably one of the important sets of slides in this class. We love recursion, and induction is going to give us a way to prove that a recursive algorithm is correct. So that is very important. That's where we're going. All right. So to get there, we need to start with sequences. Oh shoot, did I mess something up here? Okay, now it's happy. Can I select? There we go. All right, so a sequence, I'm sure you've seen this in a math class, right? A sequence is just, if you think about it long enough, it's really just secretly a function. It's a function whose domain is a set of consecutive integers. Maybe it starts at 0, maybe it starts at 1 or something. But for example, I'm sure you should have seen by now, right, the Fibonacci numbers. And it's a sequence. The first term in the sequence is 0. Like the first number in the Fibonacci sequence is 0, then 1, and then it's like they all build on top of each other after you got the first two. So it's like f of 2 is 0 plus 1, f of 3 is 1 plus 1. So it's the sum of the two previous ones. So like 1 plus 2 is 3. 2 plus 3 makes 5. 3 plus 5 makes 8. You see that? So that's a Fibonacci sequence. And if you think about it, f of 0, just saying like the first element of the sequence is 0, that kind of looks like a function. It's like define the function on the integers to just be like give back 0 when the input's 0. So like the domain of your function can just be like the natural numbers for this Fibonacci sequence. Like given 0, you better map this to 0. Given 1, you better map this to whatever f of 1 is, that 1th element of the sequence. If you see 2, like what is f of 2? What's that element of the sequence? Well, it's going to be 1 again. And then like, I don't know, 3, 4, 5, 6. It's like, all right, 1 plus 1 is 2, 3, 5, 8, and so on and so forth. And so you see it's essentially a function. So that's an easy way to think about it. Like f of 0 is 0, f of 1 is 1, f of 3 is the number 2. That's how you'll make it correspond. And so you can apply function rules to sequences. That's where we're going with this. The technical terms, I think I already gave them away. It's like each index, each element of a sequence is called a term. So like this is, I don't know, this is the 3rd term in the sequence, though the indices start at 0. So you got to keep that in mind. This is the 3rd term of the Fibonacci sequence, and its index is 2. Index into the sequence is 2. Okay, so I is the index, and each piece is called a term. Okay, so that's just some terminology about sequences. I'm sure you've seen them before in a math class, but you can think about them as functions, and maybe you've never done that before. Here's a fun meme to think about while I continue with some stuff. But yeah, let's continue with some more definitions about sequences, and that'll be kind of where we end. So a sequence, this is hopefully going to make a whole lot of sense to you. You should have seen these before, just intuitively understand them, I hope. A sequence, we say, is increasing if for every 2 consecutive indices, like you just zoom in and look at the 2 next ones, like, I don't know, here's an element of a sequence, element of your sequence. Here's like a of k, some kth element of your sequence, like it's 42. And then a of k plus 1, wherever you are, it's 44. And then you got more after that too, of course. To say that a sequence is increasing is like you look at every possible pair, like this one and this one, this one and this one. Just give them all a chance at being k, and just like look at each of them. Is it always true that a of k, like the one before, is always strictly less than the one after it? If so, that is called an increasing sequence. So if you look at the 2 elements next to each other, like that one and that one, or this one and this one, like you give them all a chance, give them all a try, and you confirm that every time the one before is smaller than the one after, or the one after is bigger than the one before, that's called an increasing sequence. So it's getting bigger each time. It's just like it's a line in that direction. All right? So that, I hope, makes a lot of sense. So an example of an increasing sequence is just like it's always getting bigger. 0, 1, 42, it can skip. 43, 47, 55, ... So it all works out. That's an increasing sequence. Next, we say that a sequence is non-decreasing if it's kind of increasing, but like sometimes staying the same. So it's like the difference is the and equals to. This one is it's always getting bigger. This one means it's sometimes staying the same. All right. So it's non-decreasing, we say. It's not always getting bigger, but it's never getting smaller. It's non-decreasing. All right. So if you look at every indice, in every pair of indices right next to each other, it's always the case that the one before is less than or equal to the one after, right? So it's like, it could be 0 and 0, 0, 1. It can kind of like stay there for a while. 4, 4, 4, 42, 43. Every increasing sequence is non-decreasing, of course. And so it's like, look at every pair. That one, this one, and this one, this one, and this one, this one, and this one. Is it always the case that the one before is less than or equal to the one after? If so, it's a non-decreasing sequence, right? So that's that one. A decreasing sequence is the exact opposite of increasing. So it's like the one after is smaller than the one before, all right? So it's like 4, 2, it's always getting smaller. So this one cannot be 2 anymore. It's got to be 1 or less. Negative 17, I don't know, you can skip. Negative 42. That's a decreasing sequence. And then I assume you can understand what non-increasing means. It's just like it's getting smaller or sometimes staying the same. So it's like a of k is greater than or equal to a of k plus 1. The next one is less than or equal to the one before it. So it can just stay there for a little bit. It could be like 4, 4, then 2, 2, 2. But it's got to get smaller if it's going to pick a new number. 1, negative 17, ... So that's a non-increasing sequence. All right, I hope that makes enough sense, but this is how you formally define it. It's like, look at every pair of indices right next to each other and see how they're moving around. Okay? So, before we go, one last definition for us today. Actually, shoot. Do I want to... Yeah, let's go here, and hopefully it'll help. So, here's a sneak peek to something that we're going to talk about eventually. It's called induction, mathematical induction. It's very powerful, but just to like plant the seed in your mind over what's going to happen here, it's all kind of about dominoes, all right? So let's pretend that we have a bunch of dominoes. Maybe you have a ton of dominoes, like a sequence of them. That's why we have to learn about this. Pretend you have a maybe infinite sequence of dominoes. You've aligned them. You're about to like knock one over, right? And assume you can do this. Assume you can prove that the first domino will fall. Like you can guarantee that this one's going to knock itself over. And then you can prove also, like you've proven that. And then if you also prove that if one domino falls, the one right after it's going to fall. So like if, just pick it, it's supposed to be generic. So if any domino falls, like if this one falls, I have a proof that this one's going to fall. If this one falls, the same proof applies and this one's going to fall too. It's like if one domino falls for any of them, then the next one will fall. What does that tell you? If you have both of these things proven, what does that tell you about the dominoes? Well, the answer is, well, if I know that the first one's going to fall, and if one domino falls, the next one's going to fall, well, the first one's going to knock over the next one. and then this applies to the next one as well. If that one falls, then the next one's going to fall. Then the next one's going to fall. Then the next one's going to fall. So like this one kicks it off, and this one keeps it going. And so we've just proven, right, forever and ever and ever until the end of time, this proves that every domino will fall. So we've just proven something about an infinite number of dominoes by not really talking about any specific, like all of them at once. It's just like we've talked about pairs of dominoes and just the first one. It's kind of weird, but very powerful that this is going to tell you that every domino falls. And that is the principle of mathematical induction. We're going to get there and define it precisely next time. Maybe not even next time, but the time after that at least. Okay, yeah, next time. Cool. But this is a sneak peek at that. All right, so this is where I want to stop for today. We're going to come back later next time and go in more depth with this. And then we'll also need to talk a bit more about sequences, though. So yeah, that's where I want to stop today. I will see you in the next lecture, and we will have some more fun.